All right, it's time. Any question from homework? Any? Oh, Aaron.
4.7, number 2.
4.7, number 2. Number 2. Find the point on the line which is closest to the origin. Nice. Okay. Find on the line y equals 6x plus 11 closest to the origin. Okay. If you find it confusing, first draw something. Try to make your drawing as accurate as possible. Roughly, it's positive, and you have a positive slope. And then whoever on this line is closest to the origin is going to be this one. So through some geometry, you can do it. It's going to be complicated. Okay, but now we have optimization. Well, let the point be xy. Okay, then the distance from this line to the origin is going to be d equals x squared plus y squared square root. And your job is try to minimize d. That's what we mean by closest. Good so far? All right. Now you have two variables. You wish your xy has certain kind of a relationship, so you can convert y to x or x to y, so you only have one variable. Of course, it's on the line. 6x plus 11. If you're on the line, if you pick an x, your y is definitely going to be 6x plus 11. So basically, your job is try to minimize this distance here. How do you do that? Well, you take the derivative, you set it to be 0, you make sure it's a minimum. Okay. Of course, to make your life easier, this is a terrible, terrible derivative to take. But to minimize d is the same as minimizing d squared. Does it make sense here? You want something to be small, you just want the square of that thing to be small. So minimizing the d is the same as minimizing this. Okay. But minimizing d squared is so much better because your derivative is nice. You don't have square root anymore. Okay. Then with all that in mind, let's just go ahead and do this, which is not hard to do. F prime x is 2x plus 2 times 6 equals 2x plus 12, 72x plus 12 times 11, 132, which is 74x plus 132. And you're wondering when this one is going to be the minimum. Well, positive, negative, so d, like that. Minimum is going to happen at here. I don't even need an interval. Okay, so that's how you are going to do it. Your point is going to be x equals negative and your y is going to be 6x plus 11, which is, wait a second, what are they asking for? They're asking for the coordinates. Well, not too bad. $66 divided by 37. 11 divided by 37. That's how you do it. That's pretty nice. Every single thing you did before in geometry now can be solved in this way. For example, if you have a line, you have a circle, okay? Find the point on the circle so such that it's closest to the line, then it's going to be this point. Now you know how to do it, right? Set it up, take the derivative, find the minimum. Find the one which is furthest. You can actually take this one, you find the maximum. Similarly, if you have a plane, you have another, I won't say plane, you have another surface here. What's the point on the surface which is closest to this plane? Again, you can take the same thing and take the derivative and find the minimum. So everything becomes super, super easy to do. That's the beauty of optimization. Other questions? All right, the exam is going to cover 4.1 to 4.7. So nothing beyond optimization is going to be covered. I would say pay special attention to how to draw the graph. That will be roughly half the exam, okay? And then how to do the L'Hopital's rule. You have all those different cases. That will be the two major focus. Of course, we have a optimization there. Okay. All right, that's all we have for exams. 4.7 is done. It's called optimization. Okay. You did some baby problems. Yeah, building the fence, whatever. It's not even fancy, right? It's simple. But now let me show you something in real life that you can use in terms of optimization, which is really powerful. Okay. And the idea is quite simple. If I give you 2 points, I would say find a line passing these 2 points. Do you know how to do it? Find slope, find a point, you have the formula. Good so far? Now, what if we have 3 points? I say find a line passing these 3 points. What's your answer? Impossible, unless you're super lucky, right? There's no guarantee they're on the same line. Makes sense so far? Okay, so in general, there's no way you can find a line which passes 3 points, but now I'm going to say, hey, if you can't do it, try your best. What do you mean by try your best? Well, find something that is as close as you can. Something like that, roughly, is going to work. Good so far? Okay, so here's the thing. How do you do this? How do you find a line which roughly passes every single one? Okay. Basically, what you want to do is you have something called y equals ax plus b. You don't know a, you don't know b. You want to find ab, right? Okay. What do you mean by the best line that fits the data? Well, if I pick this line, I'm assuming at here, your point should be here, but your point is not here, so I have an arrow. Can you see that? At this point, I predict the thing is going to be here, but you're here, so I have an arrow. And here I have an arrow. Actually, for every single point you put on, I have an arrow once I pick the line. Some of them is going to be perfect. Some of them is going to be a disaster. Good so far? So what do you mean by the best line? The best line should be the one which minimize the total error or the average error. It's fine if you did really bad on 2 points, but if you did okay on the other 98 points, I'm still going to think you're a good line. Make sense so far? So you pick A and B to minimize the residual, which is basically the error. Usually it's the square of the thing you predicted minus the real data. Does it make sense to everybody? We don't have to actually go ahead and do the hand computation. You see how this is going to be done, right? You take the derivative with respect to A, set it to be 0. You take the derivative with respect to B, set it to be 0. That's going to be your minimum. The same way we did with optimization. Then you'll find the best line. Sounds good? Okay. The same idea, of course, applies if you have 4 points, 5 points, 6 points, or 6,000 points. You can still find that line. You just have 6,000 error, and then you take the average, and then you try to minimize it. You're not going to do it by hand. You do it by computer, but it's done. But it's doable. Sounds good? This idea is called linear regression. Basically, you pick your line to minimize the error. Then it's optimization problem. Then you take the derivative. Then it's done. Okay. Now to see the real application, let's just take some workshop I did before. Usually people are charged $2,000 to go to this. And this is, I don't know, 20% of that, 15% of that. So you got $300 for free. Okay. Idea is quite simple. You have a house, okay, and you want to price it so it's sold. Well, what's the most important thing about a house? Well, the first thing came to my mind, square footage. The bigger the square footage, the better the price. Okay. So what do? I go to the history of lacrosse and say, hey, how many houses were sold for which square footage and for which price? I put all the data here. Good so far? You see a lot of points. Now what do you want to do? You want to draw a line that fits the data, which means minimize the error, which means minimize maybe, I don't know, 200 error here. That would be the best line. How do you do it? Use optimization. Take the derivative. You have 200 derivative to take. Again, done by computer. Okay, set it to be 0. You find the minimum. Good so far? Now, what's the price for this house? I'm just going to predict this on here. Is it accurate? Well, more or less. Sometimes it's bigger, sometimes it's lower, but roughly that's the same idea. Make sense so far? Okay, so that's already very powerful if you have one square root footage and the sale price. Now the interesting thing here is you don't have just square footage. You have number of bedrooms, you have number of bathrooms, you have number of square footage, you have the year built, you have whatever feature, you have brick house, things like that, a neighborhood, right? So how do you do that? Well, you just add more variables in. Use the same procedure. You have something like this. Again, now it's impossible to draw the graph because you have multi-dimensional thing. But more or less, you will know the slope. The slope is going to be, actually, let me make sure. The slope is going to be here, 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 and here. You just have a lot of slopes because every single variable has a slope. Okay, but what does it mean? It simply means this. You add one more bedroom to your house, you can sell for $4,000 more. $4,136 more. If your house has brick, you add $17,000 on it. Okay? Every single square footage, on average, of course, add $53 to your house. And we did have 3 neighborhoods. If you think that the first neighborhood is neutral, then the second neighborhood is bad. If you're in the second neighborhood, minus 1,700. But if you're in the third neighborhood, you add 20,000 to your house. Okay? It's still doable. It's just harder to draw. Make sense here? Okay, so that's the power of linear regression. Can I do it for cars? Well, I went on KBB. I got probably like 112 used the Toyota price. Okay, again, we have a data. We have the price. We have the age of the car in terms of month. We have the kilometers, fuel type. We have 3 fuel type. I don't know what CNG is. I know diesel. Okay, horsepower. Matte color means when people come here, they want a red car. You end up meeting that red car, or actually you give them, say, hey, I don't have a red car, but can I give you a blue car instead? Okay, automatic or manual. CC should be the size of the engine, the liter. And then doors, which is interesting. I got something which is 3-door. What is a 3-door? It's going to be a 2-door. Does the trunk counts for 1 door? I don't know. Yeah, 4-door is like standard. I've seen Hyundai before, which they have a 3-door. I don't know if you guys have seen that before. On the left, they have 1 door. On the right, they have 2 doors. It's a very, very weird car. But and the weights. Okay. Some rough plot. You can see a lot of cars are sold at roughly 90,000. You see a clearly trend, a linear trend between the price and the age. The older the car, the lower the price, and I think you can fit a line already, right? Goes down, which tells you the slope. Kilometers and price. You can see at first when you buy a new car, okay, the price dropped like dramatically. The first 5,000 miles you put on the car, basically every mile worth $1. Okay, you drive a new car, and then you drive a car which has been driven for only 5,000 miles. The thing dropped for $5,000. Usually, that's how we calculate that thing at dealership for normal cars. For luxurious cars, it's going to be even more dramatic. But after that, you can see a clear trend. After maybe 30,000 miles, Toyota did a pretty good job. See, their price doesn't drop that much anymore, starting from $30,000, 30,000 miles. Okay, you can do it for Ford, especially Focus. That thing drop like crazy. Okay, and then you have automatic, nothing special. Toyota doors. The more door you have, the more price. Roughly, you got some 5-door car here, which was sold really, really expensive. Probably Land Cruiser. And then you do the same thing as we did before. Linear regression. What do you have? People don't care about if you met the color or not that much. Every 1 more month you put on the car, the price dropped by $122. Every 1 more miles you put on the car, actually every 100 more miles you put on the car, the whole thing dropped for $1.6. Sounds good. With everything here in mind, have you guys actually been to the dealership recently? Before you go there, they got a salesman there. They dress really nicely. They actually go there and they try to rip you off, right? Basically, that's how you feel like, yeah, you're trying to get the money out of me. But now, if you go there, as you can see, they don't negotiate with price anymore. Have you been there before? A lot of them don't negotiate with price anymore. They just say, this is the price. There's no room for negotiation. There's no deal. There's no anything, okay? It's actually determined by an algorithm. And that is actually the algorithm, roughly, what's behind in the system. So now, because the salesman does not connect the price they sold the car with their commissions, they can actually better serve you instead of ripping you off. Because no matter how they do it, they're going to sell the car at the same price. Okay, so that's actually where the whole thing is going. And of course, we see something really, really interesting here. Can you see what's going on? The heavier the car, the more the price. Okay, according to your model. That's what mathematics tells you. Does it make sense? But it doesn't mean that you become a salesman, you go there and say, hey, look at this car. It's actually 4,000 pounds. You can not buy anything heavier in this range. It's worth the money. No, that's not the reason why the car is expensive. The reason is because the heavier you are, the better the configuration you are. So it's not the weight which sells it more. It's actually the configuration. Okay? So mathematics only tell you one side of the story, but in order to make sense in real life, you have to go dig deeper into those. All right. Does everything make sense for linear regression? You can already see that thing is quite powerful. Actually, if you are going to go into business major and try to build some model to predict anything, for the more than 90% of the time, the chance you will be using a linear regression. It's just like how many variables are you going to use? Okay, it's all about summarizing the data and making a prediction. The idea behind it, optimization. Pick the slope to minimize the error, period. Sounds good? That's linear regression. The idea is try to pick some parameters to minimize the prediction error. Linear regression is great. Do you have anything else which does the same thing? For example, if you have a system by setting parameters of the patient to predict do they have cancer. Okay. You are going to have a prediction, and your prediction is going to have an error, right? Once you have the error, minimize the error. You got the best model. Okay. Can you have an algorithm to tell you which email is spam or not? Again, you predict spam email and you let people actually click, do we have a spam email or not? In this way, you know, did I make the right prediction? Did I make the wrong prediction? Okay, do that for enough time. Imagine you're Google. You're actually having millions of emails coming to you every day. You know you predicted right or wrong. With that massive data, you can adjust your model. You can make perfect prediction almost. Sounds good? Again, optimization. Number 3, the easiest one. Take an image, okay, from the camera. You mount it on your car. You predict, are you going to turn left? Are you going to hit the brake? Basically, you predict how to drive. And you don't have to do it from the image. You can do it from LiDAR, which you take in all the information from GPS. You take information from the sound, from the weather, from the sauna, from the pedestrians. Make sense so far? But all you need to do is just put in the data, predict how should I drive, and of course you make mistakes, right? Then how do you do it? Optimization, minimize your prediction error. That's how self-driving car is done. Make sense so far? So if you go into the society and you look at all the fancy words about big data, you look at all the fancy words about artificial intelligence, machine learning, basically what they're trying to do for now, for this generation, is they're trying to do a giant optimization. And the goal is quite easy. Try to minimize your prediction error in order to produce the ultimate prediction machine. Okay, predict the sale for next month. Predict which machine is going to fail. Predict what the stock's price is going to be tomorrow. Predict how should I drive a car, under which condition. You take in the input, you produce the output. And all the algorithm is trying to do is trying to minimize the error. Sounds good? For this era, it's a little bit different from before because now we have massive data. When we do points, we are talking about millions, billions of points per day. We're not talking about small model. We're talking about big machine learning model, which has billions of parameters there. Okay? But ultimately, you just need to take derivatives from billions of times. That's basically what you do. Okay, that's how it's done. Okay, so that's roughly what optimization is in real life. Another interesting type, which is called discrete optimization, which we won't touch too much here. That is, what if you cannot take the derivative to find to minimize something? For example, how many people should I hire to maximize my profit? You cannot hire a 2.36 person. Make sense here? It's either 2 or 3. You need to hire a whole person. In that way, your function is not continuous. It's not even defined everywhere. It's only defined on integers. Make sense so far? So that's another type of optimization, which is done in a different way under the same framework. And one typical example is going to be, actually, how do I do this? It's going to be delivery robot. Have you guys seen the Amazon warehouse robot before? Okay, roughly that's actually where the optimization is. Share here. And it's just another type of optimization, except you don't have anything continuous. You have to do things in integers. You can see, like you have every spot named by an integer. I've seen people. I actually went to Fresno in Winona and see people doing things similar to this. It's really hard to call the human intelligent in this kind of scenario. You feel like the machine is smarter. The only reason human is there is because human is cheaper. They don't want to build a machine to replace this part. And think about how many people do you need in order to run this warehouse. Just try to count how many are there. Yeah, when I was there, I feel pretty sad. Like you just do this thing for 8 hours a day, and you got 16 days off a year, and the pay is not bad, but still. Isn't that beautiful? Everything is organized by machine. They schedule the whole thing. Yeah, again, that's what human does. Okay. I will try my last time to see if I can find this. If I couldn't, then I will do it next time. Oh, where is that one? No. And this is actually pretty interesting too. It's automatic parking. So you just drive a car there. They're going to go there and park for you. But which is the one? Yeah, this one. Look at that. Every single hole here has a belt connected to a particular truck going to a particular location. That's automatic charging. Another optimization problem you can think about is how many chargers do you want to put there, and where do you want to put it? Okay. All right. That's everything about optimization in your real life. Actually, if you go think about it, as long as you are starting talking about efficiency, it's basically optimization. By the way, think about how we are going to live with machine. How many people are going to lose their job due to this? If you're interested in that topic, there is a book called The War on Normal People by Andrew Young. He's really good at talking, but he doesn't know the text that well. So some of the stuff he said there is not too accurate, but the data are true. There are 5 major jobs in the United States which hires more than, I think, 30 or 40% of people, which are retailers, cashiers, retailers, restaurants, manufacture, food, and finally our truck drivers. Okay, they hire a lot of United States people as employees, and now they're going to be automated one by one by machine, and some of them has already happened. Especially customer service. If you think about it, you don't actually talk to human for customer service too often nowadays. Everything is automated. Okay, and then manufacturers, and then cashiers. Manufacturers is another one. So where will all the people go once they got laid off by the machine? Okay, and eventually, if everything is replaced by machine, nobody's hired by anybody. Who is going to buy? Because they don't have salary anymore. Okay, so again, I still don't have an answer for that. Andrew Yang thought you can give money just to people for them to buy in order to stimulate the production. But still, I don't buy that idea. That thing can work probably within, I don't know, 2 or 3 years, but long term, that thing is not sustainable. So yeah, give it some thought if you're interested. All right, that's all we have for optimization. 2 more sections, and this chapter is over. Newton's method. What is Newton's method? It's a method to solve equation like this. Do you recall we had something like this before, which we cannot solve an equation? So instead we do an approximation. Try to think about this. We know there is no cubic form. There is cubic formula, but it's hard. But instead, what we do is we just do this. Let F1, F0, therefore, there is a root due to the intermediate value theorem. Make sense so far? It's continuous and everything. Okay. After that, what do? We do F1 half. Okay. If we calculate what F1 half, okay, which is less than 0, then we know actually we can start from this one. We narrow it down to be between 0 and 1/2. Still okay? Then you pick the midpoint. So you start with an interval. You pick half the size, and then you cut here, try to see, and then you pick the next one. And you cut here, you pick the next one. So eventually, as you keep going with this procedure, what happens is in the end, you have something really, really tiny. Okay? And your solution, you know it's in there. And because the interval is so small, you don't even care which point you take. You just say, well, take any point in this interval. It's going to be accurate up to 8 digits or 16 digits. Okay, that was called bisection method. Which give us a new idea. That is, you do a simple thing. Multiple times, 1,000,000 times if necessary. You won't be able to find the solution, but you will have a nice approximation, which is very, very close to the solution, but never the same unless you're really, really lucky. Sounds good? Okay, this is great. You can program this one in the computer to do it for 1,000,000 times. You can solve any equation basically, but it's slow because your precision only improves by half every single time. If you want a really nice precision, you probably have to do 100 times. Okay. Now we want to introduce the Newton's method, which will be way faster. This is the idea. Let me draw the graph first. Let's say we have some random function like this. All right. Now, I want to know where this solution is, but I don't. Instead, what I will do is, number one, I will pick AX0. Any X0, just pick it randomly. I will pick it to be here. Okay. Number two, I will find the tangent line or linearization, whichever way you name it. I call it LX. Good so far? Now, fx equal to 0 is really difficult to do. There's no way I can find 0. But Lx equal to 0 is really easy to solve because it's just a line. Do you know how to find where the intercept of the line is? Just set y to be 0 and solve x. Good so far? That means I will be able to find this point. Okay. I start from something called x0. Now I end up at something called x1. Make sense so far? I'm not done, but what I claim is x1 is better than x0. It's closer to the real point I want. It's closer to the black dot. Sounds good? Now what I'm going to do is I'm going to repeat this process. The only difference is I won't start from x0 anymore. I start from what I just find. I guess this is not copy, paste. What am I going to do? I am going to forget about everything I just did. Just pretend I started from x1. Okay. I do the same thing. Find the line, tangent line. Good so far? Still, I can find 0 here. That's my x2. Do you agree x2 is even better than x1? What if I take x2, go to the function, do the tangent line again? To find my x3. If not happy, x3, go there, do the tangent line again to find my x4. I just keep repeating this process. Can you see that eventually this one goes to the root? And according to what I just draw, for this case at least, it goes to there really, really fast. Is the idea clear? By graph. And basically the words is just what I summarized, right? All right. Now I'm going to take this one. That's what I just summarized with words. Let's polish it a little bit. Number one, it's not going to be x0 anymore. If you start from x0, you can produce x1. You start from x1, you can produce x2. You start from x2, you can produce x3. If you start from xn, you do it at xn, you can find xn plus 1. Okay, how do you do it? Well, first, you have xn. You find the tangent line at xn. Well, that's pretty easy. You need a point. You need a slope. Okay. Then Lx is just y minus That's the tangent line. Next, what do? You find x to solve Lx equal to 0. Then you just set y to be 0 in this. That gives you negative fxn equals f prime xn x minus xn So if you set y to be 0, you find your x is this. Number 4, this is how you produce the next one. This summarizes the whole procedure I just described by words. Good so far? All right. Once you find this one, you can put this one back into this position. You can find xn plus 2. Once you find xn plus 2, you can put it in. You find xn plus 3. You just keep going. Produce one more, after one more, after one more, after one more. Just keep going. According to what we just draw, the more you do, the better the result become. Sounds good? That is called the Newton's method. Idea is quite simple. Pick the first point. Number 2, calculate the second, the third, the fourth, and keep going using this formula. Okay? Repeat until you're happy. Technically, you should repeat until this one converge, but we haven't defined what we mean by converge yet. So just repeat until you're happy. Later, we will show how to decide if you're happy or not. Pretty ironic, but yeah, we have a way. Sounds good? Let's see example. Okay, let's solve it using Newton's method. Step 1, pick an initial value. Any preference? If no, let's pick it to be 0. It's easy to compute. Don't do 72. 72 is a disaster. Okay, so number 2. Xn plus 1 equals this. What is your fxn? Fx is x cubed minus 3x plus 1. F prime x is this. Okay, now, according to these two, x1 is going to be x0, which is 0, minus f0 divided by f prime 0. Sounds good? Can I do the second? Same formula, but instead of putting in 0, you should put in 1/3 now because you're putting in x1. Okay. That's your x2. Sounds good? X3, well, same procedure, but instead of putting 1/3, you put this, the one you just find, 25 divided by 72, you find x3. That's gonna be something we don't wanna do. Okay, after that, take that number, put it in, you find x4. You keep going. Is the procedure clear? Now you want to take out a calculator or program it because you really don't want to do this by hand. Okay, so let's take it and let's do it. Okay, we start from 0. We do it for 10 times. We take the next one to be the previous one minus fx divided by f prime x. We do it for 10 times. After the first time, we got 1/3. After the second, we got 25 divided by 72. After the third time, we got this, and then the fourth, the fifth, the sixth, and keep going. Sounds good? Are you happy? You should be happy after this, because after that, yeah, this one doesn't seem to update anymore. So that's roughly where we end if we only need 4 digits. Sounds good? I didn't print them out. Actually, from here to here, it's still changing, but it's not at the 4th digit. It's maybe at the 10th digit. So if you're not happy, just do it one more. You will see, like, at least you're accurate for at least for the first several digits. That's an indicator that you should stop. Is it correct? Well, let's see. 3473. Zoom in. 347. Okay. Three, 4, 7, 3. Okay, so it's actually very, very accurate after you do it for 3 times. Does everything make sense here? Okay, that's how you do Newton's method. Okay. Quick summary of what we just did. Okay. How do I draw it nicely? Okay. That's roughly like it. So what did we do? We take 0. We did the tangent line. Okay, the way I draw it, we probably hit it the first time. But either way, we draw the tangent line, we find, okay, where our point is. That's our x1. You do it again, you find x2, you do it again, you find x3. So that's how we did it with Newton's method. All right. That's it. That's all we need for Newton's method. Some comments. Number 1, it's really fast. So it's a preferred method in real life. Number 2, I have a question here. We start from 0, we find within 3 steps, we find a pretty accurate estimate of this 0 here. Good so far? Do you notice this one still have 2 other roots? Here and here. Does it mean that Newton's method cannot find them? Well, how do you modify what we just did in order to find these 2? I don't want this one. I want these 2. If you feel confused, try to draw a little bit. You take a point, you do the tangent line. How do you get these two? Instead of this one. What matters? Can you see the reason you got this one is because you picked 0 as your starting point? What if you start from this point? Then probably you will end up with this, not the other one. What if you start from here? Then maybe you're going to end up with this. So from here, you can see if you have multiple zeros, your Newton's method can converge to either of them. And the key to control it is x0 determines which one it goes to. So you probably want to play with your x0 a little bit. Once you have that, the whole process is automatic. Then you are stuck with one of the answers. Okay, so your freedom goes there. Aaron?
Now for that, what if your x0 is like a critical point where it's right in the middle of a maximum or minimum?
That's beautiful. Number 3. Will this one always work? Well, what can go wrong? Look at this formula. Not this. Critical point means what? Right? If that happened, can you still use this formula? You basically have a fraction you're dividing by 0. It's not going to happen. Judging by the graph, it basically means you're here. You do the thing, and you find your tangent line is flat. Remember, your goal is try to actually let your tangent line intersect so you can find this one to be your next point. But if it's flat, there's no way they're going to intersect, so this method fails. Okay, so Newton's method may fail. And what you said is exactly one possible cases. You don't have to be so lucky that you just pick x0 to be the bad one. It's possible your x5 is the bad one. But before you do it, you never know. Right? But usually that's great because, we have computer. Computer will tell you an error that is you're dividing by 0. Please reconsider what you're just doing. Okay, so we do have techniques to try to avoid that, but this may happen. All right. I think we have 1 minute left. Let's just quickly show the example. I really don't want to pull this out next time. We said it's just depending on which one you pick. You pick 0, you end up with 0.3473, right? If you start with -4, you end up with the other solution. Okay, you start from 3. You end up with the other solution. Sounds good? So actually, you need to be a little bit smart before you start this thing and try to pick the correct or the desired initial value to start with. Otherwise, you may have a 0, but that may not be the 0 you want. Okay. All right, that's all for today.